of this afternoon will be given by Hiroshi Kera on approximate computation of vanishing ideas.
Yes, so thank you for introduction. So I'm Hiroshi Kera from Chiba University, Japan. So today I'm talking about approximate computation of vanishing ideas. And this work is jointly done by Elias there, and also Sebastian. Okay. So first I give some definitions and notations. So in this talk, we work on a polynomial ring over R, so which is denoted by P, and P denotes the set of terms. And we handle data sets, so X is a set of samples of n-dimensional points of n dimension. And vanishing ideal of points here, vanishing ideal of X is a set of polynomial which has all polynomials that vanish over X. So if given any point in the data set, the polynomial should vanish for it. Okay, so graphically, as you can see on the right, so if the data set consists of 3 samples, then any polynomials whose contour pass through the samples are vanishing polynomials. So vanishing ideal is such a set. Okay, so and just in case, so generator of vanishing ideal is okay, so the G is is a set of generators that generate vanishing ideal I of X, which is that set. Okay. Okay. So, and one more slide for definitions. So we define here evaluation vector, which is so evaluation vector G of X. G is polynomial and is n-dimensional vector. So and the ith entry is the evaluation of polynomial G at Xi, the ith sample. Similarly, evaluation matrix of a set of polynomials uppercase G is defined as a matrix whose ith column is the evaluation vector of ith polynomial in the set. And then now we have important notion epsilon approximately vanishing here. So polynomial G is epsilon approximately vanishing over X if and only if the following is satisfied. So we calculate the evaluation vector and then calculate the 2 norm of it and then divide it by square root of m. And then if this quantity is less than or equal to epsilon, then we think of it as approximately vanishing over X. Okay. So I said set of X is data set, and then so in many applications, data set is perturbed by noise. So we don't consider exact vanishing. We want to consider approximate vanishing so that we can avoid overfitting the data set.
What is the motivation for exactly this scaling to make it also approximately vanishing?
Which scale? So this one?
So you have like 1 over root m, and then you do the like the normal GLX, the 2 norm.
Yeah. So intuitively, we want to say if polynomial G takes small value for every single point, then we want to see it as vanishing polynomial, approximately vanishing polynomial. And we use 2 norm just because it's convenient for computation. And then we use the scaling, which gives which gives us some bound that is independent of the number of samples. So we're just taking the average. Okay. Okay. So now here is the example from machine learning. So in most cases, we are trying to use vanishing ideal computation for machine learning. So we use we introduce epsilon approximately vanishing because we want to handle noisy data set in machine learning. So I give some binary classification example here to motivate why we want to calculate the generator of vanishing ideals. So here is a dog or cat classification. You have several images which can be dog or cat, and then we want to label them. Okay, and then in machine learning, you have many ways to do binary classification. But if you want to use some computer algebra for this task, then what you can do is to compute the approximately vanishing polynomial. So it's like this. So you have a polynomial g, and then you you try to find approximate g, which is approximately vanishing for dot class, which means if you feed dot image to the polynomial, then it outputs some small values, and otherwise it outputs some large values. So we want to find such kind of polynomials. And actually, there are several applications in various fields: machine learning, computer vision, like signal processing, computer evolution and computation, and so on. So so I said there are many ways to do binary classification in machine learning, but why do we want to calculate approximate vanishing polynomial is that if we consider polynomials, then we can result to some strong assumption, which is called an algebraic set assumption. So usually in machine learning, people assume data comes from some low-dimensional manifold, which is everywhere smooth, but data can come from some space which has singular point. So we want to consider algebraic set, and then actually there are several words that if we assume algebraic set, data comes from algebraic set, then we can prove something good that cannot be proved by assuming manifolds. Okay, so here is the example. One is classification. So under some conditions, we can extract linearly separable features, which is very nice because we can use linear classifier after this. And also in semi-supervised learning, some people prove that so semi-supervised learning can be unboundedly better than supervised learning, which means that in semi-supervised learning you have a labeled data set, but you also have unlabeled data set. Okay, and then the question is whether this unlabeled data set is sufficiently helpful or not. And this some criterion which says if this criterion is met, then we can say, okay, these unlabeled samples are very helpful, and which is what it says by this. So if we assume data points comes from algebraic set, then we can prove that semi-supervised learning is more powerful than supervised learning, as we expect. And the similar things is said in clustering. Okay, so the pipeline of vanishing ideal computation is like this. This is kind of summary. So we have a set of points, so which is called data set, and we assume these points come from algebraic set, which is represented by the zero set of polynomial system. Okay, and then of course we have many polynomial systems that can describe this algebraic set. So we consider vanishing ideal, which contains all possible vanishing polynomials over
Can I
X.
ask a question?
Yes.
So here X is the finite set or
Yes.
X is the model that you assume?
Yes.
So was X in the surface or the finite set?
So X is usually we have finite number of sample training sample, so it's finite.
Yeah.
But in machine learning, typically data comes from some smooth, not necessarily everywhere smooth, but typically smooth. So we want finite, we want generators for finite dimensional ideal. So the data gap. So what we have is the algorithm for zero-dimensional ideal, but what we want is the algorithm for positive dimensional ideal. So there's a gap, and this is kind of future work. But in many cases, you perform the algorithm for zero-dimensional ideal, and then if you terminate in the middle, then you can get the generators for a positive dimensional ideal. Yeah, but it's not perfect. I know. Yeah, thank you. Okay. So so we consider vanishing ideal, and then we know that the vanishing ideal always have some finite set of generators. So in the end, we aim to calculate a set of generator of the vanishing ideal of samples. Okay, this is the definition. Okay, so and then so in particular, I put approximate there because, as I said, the data set is typically noisy, and this is kind of young topic. Young topic, and then it's only people start talking about approximate computation of vanishing ideal in the last decade, but there's a lot of algorithms developed. Okay, so this is history line. And originally the topic has started in computer algebra. So I think the first method is Buchberger-Muller algorithm there, 1982, and which calculate a gravinar basis of vanishing ideal. And after that, the variant of Buchberger-Muller algorithm was designed for calculating a border basis, which is known to be more numerical stable than gravinar basis. And then in 2009, the approximate vanishing ideal algorithm is developed, and then people start talking about how to handle noisy samples. Okay, and then you can see there's some green part, and which is machine learning part. So at the beginning, this kind of topic was developed in computer algebra, but Livni introduced this notion into machine learning, and actually this VCA, Vanishing Component Analysis paper, got awarded as best paper award or best student award. I forgot, but anyway, some kind of best paper in ICML, one of the top conferences in machine learning. So the critical difference between them is in computer algebra, people are very strict to theory, but in machine learning, we don't care that much. So, but instead, we want to, we need some good performance in applications. And then one critical difference between them is in the vanishing component analysis, they don't assume term ordering, monomial ordering. Monomial ordering, because monomial ordering, term ordering is perfect in theory. You can choose whatever monomial ordering, it doesn't change any properties in theory, but different monomial ordering can give you different results, which is not very happy in applications, because you never know which ordering is the best. And after that, there has been several works in machine learning, and very recently, I propose some variant of vanishing component analysis, and Elias, they prove some nice generalization bound, which gives some guarantee that if you fit to your training data well, then you have some guarantee that it also fits well to some future samples. Okay. So the blue part and green part can be rephrased in this way. So we have two types of algorithm. One is developed mostly in computer algebra, and the other is developed mostly in machine learning. And the first one can be said monomial aware algorithm. Okay. So why is monomial aware? It's because polynomials are regarded as linear combination of monomials. Okay, and then people typically do symbolic computation. And then on the other side, monomial agnostic algorithm is that the algorithms that construct polynomials by linearly combining polynomials again. So in this talk, I mostly talk about two things after this. So the first one is Oracle approximate ideal algorithm, which comes with some nice generalization bound. And the other one is the method that solves a spurious vanishing problem in monomial agnostic algorithm. Okay. So first I introduce the overview, the method of approximate Oracle, this OAVI algorithm. Okay. So here X is again set of samples, and C is okay. So this is the some part of Oracle ABI or ABI algorithm, and then in the next slide I will give some overview. But just okay, this is some subrouting. Okay, so C is a set of terms. Okay, and B is the term which is greater than any of the terms in C, in the sense of ordering sigma. So we have some monomial ordering. Okay, we assume some ordering in monomials, and then D is the greatest term in that sense. Okay, and then next we solve some regression. Okay, so here I use the notation of evaluation vector. So we evaluate monomial B there, B of X. Okay, and then we evaluate the terms in C, so C of X, this is evaluation matrix. Each column is the evaluation vector of each term. And then we want to find some nice coefficient, okay, V. And then we solve this regression problem and then get some R star. And this R star gives so by solving this, you can get R star approximately vanishing polynomial. And then the polynomials is G equals B minus the summation of the term Pi. Okay. So you get this coefficient Bi by solving this regression problem. Okay. So now it's the overview. So I'm not very sure whether this is clear enough, but the overview is something like this. So input is a set of samples, X, and some approximation tolerance or approximation parameter, epsilon, and term ordering sigma. And then output is G, a set of epsilon approximately vanishing polynomials, which becomes a generator of generators of vanishing ideal when epsilon equals 0. And then F is some is a set of epsilon vanishing polynomials. Okay. So we start with degree 0 case. We construct polynomials from degree 0. It goes from degree 0, degree 1, degree 2, and so on. So and then this graph shows the let's think it as the exponents of the monomial. So we consider a bivariate polynomial here, and then at the origin we have 0, 0, which means the monomial 1. Okay, and then F is initialized as a set of just it has 1, and then next at the degree 1 we have this. So according to the ordering sigma, the next term we target is Y. Okay, 0, 1 is Y. And then we solve this linear dependency test. We solve the regression problem and see whether this Y can become a leading term of vanishing polynomial or not. So we solve the linear regression problem and then check if this R star, the residual, is greater than epsilon or not. If R star is greater than epsilon, then which means we couldn't find good approximately vanishing polynomial. So we append this B, in this case Y is B. We append this Y into the set of F, into the set F, and then otherwise, in other case, which means we can find some nice approximately vanishing polynomial. So we append this polynomial into the set G. Okay, and then things go similarly. So okay, so this is in this case we assume so Y didn't give any good approximately vanishing polynomial. So the F is now becomes 1 and Y. Okay, and then now we check X. Okay, so we check X and then we do similar things. We solve similar things and assume that okay, now we get some good polynomial here. Okay. So we keep going. So at the degree 2, next we check the terms in degree 2. Okay, so we check y squared, xy, but we don't check x squared because we have already got polynomial whose leading term is x. So it doesn't have to check s squared because if we can get vanishing polynomial generator with leading term s squared, this can be divided by by G1, so we don't need it. So we don't check x squared. This is how we restrict the number of polynomials to check. Okay. And then suppose that in both cases, we got approximately vanishing polynomials. So now in set G, we have 3 approximately vanishing polynomials, and then so all border part are now in black. So we don't we terminate it at this point. So this is the overview. Okay. So this is a generalization bound. So recall that, so OAV algorithm gives a set of epsilon approximately vanishing polynomial. And what is proven that is that suppose that the support of the distribution of samples is from -1 to 1, and then epsilon is 0 to 1, and tau is some positive value, and then k is a non-zero natural number. And then X is a data set, and which is sample from distribution D. And then in that case, for any delta, any positive delta with probability -1 minus delta, so this inequality holds. So what this inequality means is that, so you can see on the left-hand side, this is the gap between the expected extent of vanishing on the left, and then on the right, you have empirical extent of vanishing. So this is, in other words, this is the gap between test error and training error. Okay, and so this gap is upper bounded by some quantity, and which is kind of how to say complicated, but you can see, for example, the number of samples is m there, and which shows that if the number of samples increases, then the upper bounds goes down, so it becomes tighter and tighter. So intuitively speaking, like if we have more samples, then the gap between test and training becomes narrower. So it's intuitive. And the same can be said for tau. The tau is the strength of the regularization. So if we have stronger regularization, then we don't have a large gap. So it looks a little bit complicated, but basically this is what it says.
Can I ask a question?
Yeah.
Where do you use the fact that the G's are polynomials? Polynomials of the given group. That is.
In this case, we don't have the G does not have to be polynomials necessarily, but yeah. But I think it's the other way around. Like we have some algorithm that calculate polynomials, and then we want to know the how to say the generalization bound. Yeah. Yeah. So so actually what the technique we use for proof is very standard in a sense that very standard in machine learning that proves some generalization bound. How many minutes left? Thank you.
23.
23 minutes left. Sorry, I forgot mine.
Yes.
Okay, thank you. Okay. So we finished the first part. Okay, and then the second part is monomial agnostic algorithm. So here you don't get access to monomials. The polynomials is constructed by a linear combination of polynomials, and each polynomials, in this case, each polynomials could be some products of polynomials. So it's very complicated. So in this case, we encounter spurious vanishing problem. Okay, and then we need some normalization. Okay, so these slides explain why normalization matters in approximate vanishing computation. So the problem is called spurious vanishing problem. So it's very simple. So what it says is scaling can turn any non-vanishing polynomial into approximately vanishing polynomial. So for example, at the top row, you can see polynomial G1, the zero set of it is like a circle, which is approximately passing through the sample in the blue dots. So this is approximately vanishing polynomial. So, and this is what we expect to approximately vanishing polynomials. But and in the second row, you can see G2, and this polynomial, the zero set does not passing through the samples at all. So it's non-vanishing polynomial. Okay, but if you divide this G2 by some large constant, then suddenly it becomes approximately vanishing polynomial, because by dividing by large constants, all the coefficients become very small. Okay, so the polynomial is very close to zero polynomial, of course. So the typical solution is coefficient normalization, of course. If you normalize the coefficient vector, then the problem is solved. But the question is whether this is the best normalization. Okay. And then to think about it, coefficient normalization has several limitations. For example, I said we are now interested in monomial agnostic setting, but coefficients, to get access to coefficients, we have to be aware of monomial. So in general, in monomial agnostic setting, we cannot calculate the coefficient, the norm of the coefficient vectors. Okay, we cannot get the coefficient vector. And also, even if we can get access to coefficients, the number of coefficients grows very quickly, because the number of monomials grows very quickly. So in monomial aware setting, as I show in the overview of OAVI algorithm, by using some term ordering and with some tricks, you can avoid handling all possible terms. So you only have to consider as a restricted set of terms. But in monomial agnostic setting, you have to handle all the monomials. But first, you cannot get access to the coefficients. Even if you can, it's computational costly. Okay. And also, recently I proved that that ABM algorithm, which is kind of sibling of all ABI algorithm, but ABM algorithm cannot find high degree generators. Generators of high degrees. Yeah. It's intuitively because, for example, you have univariate polynomial g of x, which is x to d, and then if some data range from -1 to 1, then with sufficiently large exponent, then this x to d becomes approximately vanishing polynomial. Even this is coefficient normalized. Okay, so instead, now here is the monomial agnostic normalization. So, which is called gradient normalization, which is very simple. So for non-constant polynomial g, then you normalize g so that it has this quantity to be 1. So the sum of square sum of the LQ norm of the gradients at each point divided by the square root of n. So in general, what it says is that you try to keep the gradients at sample to be not to be too flat. Okay, so if the gradient at every single point is flat, it's we suspect that this polynomial to be zero polynomial. And another intuition for this normalization is that because intuitively you divide your polynomial g with its derivative, so it gives some linear behavior. So which relates to the property I will introduce shortly. But of course, the concern is that so the concern is that even non-zero polynomial can have this quantity to be zero, because this g can have the gradient zero at every single point, even if this g is non-zero polynomial. But unfortunately, we can prove that if we need this polynomial to form our generators, the set of generators, then we don't need this. This g has non-zero of this gradient norm. Okay, so if this g is the gradient of g vanish at all sample, then we don't need this g. So this normalization is valid in our vanishing ideal computation. So the other property that can be achieved by gradient normalization but cannot be achieved by coefficient normalization is scaling consistency. What it means is that, so you have a set of sample x, and you can also have a scale sample alpha x. So alpha is some scalar, then you just scale every single vector in x by alpha, and then which says then we can get similar generators. For example, similar sets of generators. For example, the number of generators in the sets G and G hat are the same. And also between G2 for a GI and GI hat, then we have some explicit relations given here. That's if we represent GI as the linear, is a combination of HI tau, which is the degree tau part of GI, then GI hat will be represented and can be represented in this form. So this is symbolic relations, symbolic relation. And as for numerical relation, we have this. So GI hat of alpha x equals alpha times GI of x. So it looks like a linear relationship. This is what I meant, linear behavior at this point. Okay. And you can also prove that coefficient, if you use coefficient normalization, then you cannot achieve that. So if alpha is greater than or smaller than certain value, we can prove that, greater than or smaller than certain value, then the G and G hat does not have the same number of generators. But this is kind of weird because the scaling does not change any fundamental structure of samples. So scaling consistency is achieved only by gradient normalization so far, and not achieved by coefficient normalization. Okay, so here is a summary. In this talk, I talked about approximate computation of vanishing ideal, and the pipeline is like this. And then so far, there are many challenges in this topic, and then it only has about 10-year history, so it's not very matured yet. But so far, we provided a generalization bound, which is very good in machine learning, generalization bound under coefficient normalization. We also provided that gradient normalization, which can be replaced with a coefficient normalization, and this normalization can do what coefficient normalization cannot. But there are still many problems. For example, we don't have any generalization bound under gradient normalization, and also the computational cost should be reduced more, especially in terms of number of variables. And also, if you want to work on machine learning, then deep neural networks is very popular. So it's very nice if you can extend this kind of notion to deep neural networks things. Okay, thank you very much.
We have time for questions.
So do you believe there's a cat's manifold or a dog's? Is there a cat variety and a dog variety, which we ultimately hope to learn?
Yes, yes.
Philosophical.
Yes, I believe so. I believe so. So I'm not very sure whether this is algebraic variety or not, but because we think that, yeah, I think nobody knows, but I think it will work very well. So actually, about a decade ago, there was algebraic clustering, which assumed that different classes belongs to different hyperplanes, and the whole samples belongs to the union of hyperplanes, for example. And this is algebraic set actually, and then this clustering works very well.
Maybe I have a related question.
Okay.
So you talked a lot about machine learning. In this context, so the data are with noise, and well, they are usually modeled by some say random distribution of points.
Yes.
Like
Yeah.
you have a Gaussian distribution of points centered at some
Yeah.
with a mean, a given mean, so a point, for instance, in the plane, and you have a cluster of points around.
Yes.
So what would give your approach here? So one expect to get 1 point in the vanishing ideal here is maybe when we expect 1 point, which is this mean point. So how does it how is it working in this case? Does it work well, or what do you obtain?
So what kind of noise
So take a Gaussian distribution
Yeah,
of points around some points mu and some variance sigma.
Yeah, so in machine learning there are many different types of noise. So
Well, this one is the standard one.
Yeah, so if Gaussian noise, then one way is then we can take a mean of the neighbor samples and then average out the noise. This is one way. But I think this problem can be resolved by changing the optimization problem here. So we have a least square problem here, which is generally working well for, which is generally works for Gaussian noise, because we also have L1 regularization here. But we can also have some, for example, shock noise, which is outlier noise, not Gaussian, but mostly the noise is moderate, but at some point we have some outliers. And in that case, we can resort to robust optimization, which is well developed in machine learning. So yeah.
But what your method will give here?
Maybe I can help. So you're saying you have 1 point, and around that you have points sprinkled due to Gaussian noise, right?
Yeah. And you can maybe have some.
Yeah. So in that case, it kind of depends on the two classes in application, because if the other class is something that is distant enough to the point cloud of your one single point, it shouldn't be a problem. We get maybe an intersection of 2-degree-1 polynomials around that point, or even the constant polynomial for the 1 point Gaussian noise class. But for the other class, which might be something different, we get again whatever generators relate to that, and then you don't run into an issue. You run into an issue when these Gaussian noises are so big that the two classes begin to overlap, and it's no longer clear to what class a point belongs. But then also other methods, of course, fail because your classes in a sense overlap. Like when we want to try to classify color, that's maybe a bad example because we give an RGB value, but red and yellow, what do we do with orange? So something of that regard.
Yes. So yes, the next question is when you have several clusters. Yes. But there are methods which work, which can handle.
Yeah, but when your training data is not perfectly classifiable on its own, you cannot get perfect classification accuracy on training data. Right?
Well, you get the probabilities at the the data belongs to one cluster. Or,
Yes, but
so
if the two clusters are two lines and we have Gaussian noise in both directions, and one point from class 2 is very close to class 1 and one from class 1 is close to class 2, you can't really do better. I mean,
yeah, okay, but these are methods which are used in another context. So what I'm curious, what would give your method in this case? You will find the two centers, for instance, or you will
Yes.
find some.
yes, you would find the centers when if you tune the parameters in the correct way, the vanishing parameter epsilon needs to be chosen correctly, then you would probably find something that lies in close to those centers.
Good, so. If no other question, then thank you again.